In the conceptual level, these 3 stalks pretty similar to what we put in the beginning of the assumption. If you remember, pretty close to that. And you just change this into pipes. We call it a convert flow. Those are the flows. And then add a few parameters we need to observe. So in here, you consider how many people get sick per day. In here, you consider how many people recover each day. And then, of course, the 2 parameters is the B, we call it the infection rate, and R, the recovery rate. And the B is actually 1 over CFV. You don't take the S here. The S is right here. Once you build this conceptual model, in Stellar, you go to the mathematics model. Then you need to fill all those numbers with question marks. And the first, in the 3 stalks, we need to fill in the initial condition. That's 20,000, 1,000, 500. And then we fill this number is 1/10. And this number, you remember, is 0.3, 21,499. So once you filled this, you're ready to run the model. When you run the model, you need to make a graph, and you have 2 parameters to choose. The first, domain. If you do nothing, this is T, but the default of the Stellar is going to be from 0 to 1 to 12. But now you can change it to 0 to 120 for you to observe a long period. So that's the first change. That's in the run spec under the run menu. And then when you do the graph, you remember the number goes all the way to 22,000. You change this into 22,000. Then the graph will scale well. Well, this you really need to go through the tutorial yourself. But when you run, that's what we found. When you run the Stellar model, you get 3 curves. And the 3 curves, the first one, that's the susceptible. In the beginning, we have 20,000, high number. And infected, that's the red line, that's 1,000 here. And the recovered start from 500. And then you observed 120 days, about 4 months. Well, when you run this, of course, you need to observe. That's why it's called the computational science. You need to observe the computation and to discover what you really concern. A few questions, of course, the most concerned question is, how long it take for the majority to be infected? And how many all recovered? And when the disease, the infection rate peaked. So like this point, and when these 2 cross each other, those are the critical points you want to observe. And then you look at the shape of the 2 lines, the trend, and so on and so forth. If this gives you a big picture, an impression, you will build a table, give you all the detail, and you can roll down the table to look at the day, and this each is 1/4 day, and look at the number change. So let me give you a few questions, and just to see what you really like to discover from the running result. So first question, when does the infected number reach the highest point? Well, that's the point here. See, the maximum of the infected. And that number, not by coincidence, is the number of the infected and the susceptible cross each other. And if you look at this is 30 and here's around 18 days, if that's not clear enough, you can look on the table to find the information. Second, explain the shape of both susceptible and recovered, and what that shape tell you. Well, not only the shape, we know this is both like an S shape, so we call it a logistic curve. You remember when we talk about first population model, it's a logistic curve. But the difference is the suspected goes down with an asymptote here, and the recovered goes up with an asymptote here. So they all goes flat after pretty much after 2 months. So one is decreasing, one is increasing. They both are logistic curve. So if you are the health officer, want to make some decision, like some policy of quarantine or inoculation, you know the critical period is very clear, should be this period. So that's what you observed. And this next question. In what day the size of infected population increase fastest? If you introduce quarantine, you might think that's the most critical time. And then from your observation, that probably is right here, and right here, when the slope of both are the steepest, that's about 10 days, and you can confirm into the table. We can ask a whole list of other questions. One easy question is, if we change the initial condition, assume I introduce inoculation, and you don't have 20,000 people, you only get about 5,000 could be susceptible. So if the inoculation measure is introduced, how are you going to modify the model to make it useful? So that's another just a good exercise. Particularly, think that question, if 80% of the susceptible people are protected into the inoculation, how are you going to change your model? Well, it's obvious you need to change the initial condition. It's no longer 20,000 people be susceptible, and only 4,000 people, that's about 20% of the people who has not got the inoculation could be susceptible. Okay, you change that. However, you also need to change the infection rate. The contact may be the same, but the probability you contact to the susceptible will be changed. Why? Because this equals the total population minus 1 over the susceptible. The total population does not change. You still have the 21,499. But what changed is the S. Now the ST is no longer, in the beginning, no longer 20,000, but 4,000 to start. So all those questions, you can discuss and analyze it, then answer the question.